Okay, of course, yes. Yes, there will be a quiz. Yes, please take notes if you want to draw that. If you want to draw this. Let's see. Are they in the 2-5 position? I think so. Okay. Voila, molecule. Right. This is EGCG. What does EGCG stand for? EGCG. Molecules. Epigallocatechin gallate. You were all too shy to say that, but that's what it is. Epigallocatechin gallate. This molecule comes from green tea, and it's found in some other plants. It's one of the, Dr. Schneider and I were actually geeking out about this in our rehearsal, our run through. This is one of the master regulator molecules. This is a beautiful molecule. This helps to regulate the systems of the body. So it all starts and begins with molecules. Now, when we look at food, and the food crisis that's going on today, why is our health failing? It's because we're not eating medicinal molecules. We've gone through our analogy before about how you can go through an entire day pretty easily without eating anything medicinal. And that's a shame. Vitamins and minerals are good. They're good, and they're powerful, and they're essential. But just as essential are certain molecules. These molecules, they should, I hope in the future, will have vitamin-like status, i.e. you need to get a certain amount of these molecules each and every single day for your health. Because it's true and it's powerful. So what we do here at 3 International, we start with molecules. What's the definition of a molecule? Exactly. Bunch of atoms, technically 2 or more atoms thrown together constitute a molecule. And we have inorganic molecules, inorganic meaning not made of carbon, and we have organic molecules. So when you have intersections here where 2 lines intersect at an angle, this is a carbon atom, right? This is kind of the shorthand nomenclature that we use when we draw molecules. So everything begins and ends with molecules. 50% of all cancer drugs are molecules from plants. Did you know that? 50%. Mother Nature has a treasure trove of molecules. How many species of plants are on the earth today? 600,000. How many of these plants have been studied for their bioactive molecules? 5% or less. Good. So this is what we do here at 3 International. What do? We travel the world to find and discover beautiful molecules. We put them into products to support your health and longevity. Because this molecule is known, and it's a powerful molecule. But there's a lot of molecules that aren't known. And if we can discover a new molecule, a new nutrient, we can simplify it. When we talk with people, molecule, they might not understand. We can simplify it and say nutrient. If we can discover a new nutrient that has new results, that gives you power, right? So really what we do, we have new molecules. This is too bouncy. Equals new results. That's what we do. New molecules equals new results. So how do these molecules work? Like EGCG, my gosh, that's a beautiful molecule, right? How does it work in the body? What we do here at 3 International, so we talk about molecules, but we also talk a lot about genetics. And genetics is important. Now, when we talk about genetics refers to genes. Let me just use a different color here. So we have genes. There's 25,000, roughly, 25,000 genes in the human body. These genes are like switches that turn on and off all the processes of the body. Because the body performs millions of processes every single second. And this is just talking about the human, our bodies. What about the gut microbiome? The microbiome. The microbiome has about 300,000 genes. Think about that. 300,000 genes in the gut microbiome. A lot of times we talk about health begins and ends in the gut. Well, when you look at this, maybe that's more true than we realize, right? 300,000 genes. Now, how do molecules relate to genes? Well, let's draw a strand of DNA. We did it, right? That's a strand of DNA. Can you see that okay? Can you see that on the screen okay? No. Forget it. Okay. Let's do Can you see that better? Okay, so that's a piece of DNA. Isn't that great? It's a piece of DNA. That was easy. And then we have a gene. This is a gene. And a gene is just a segment of DNA. Right? DNA consists of thousands and thousands of base pairs. What are the nucleic acids? AGCT. Good. A for what? Adenosine. C for cytosine. G for guanidine. T for thymidine. U for, come on guys, uracil. Good. U for uracil. Right? So we have all these. We didn't think we were going to be tested, right? We're kind of pushing our limits here, right? So we have a gene. What gene should we talk about? GLP-1. Let's talk about GLP-1, right? That's a great gene. Yes! GLP-1.
GIP.
There's GIP as well. Yeah. GIP and GLP. Let's talk about GLP-1. Glucagon-like peptide 1. Right? So this gene, what does a gene do? A gene encodes for a protein, right? And proteins in the body perform a function, right? Protein does work, and these proteins then get results. And a lot of times proteins in the body are enzymes, right? And enzymes are the molecular machines that do all the heavy lifting, that catalyze all the reactions in the body, right? So this gene, it can be turned on, or it can be turned off, right? If the gene is turned off, then does it make the protein? No. If the gene is turned on, does it make the protein? Yes, right? So, but how does this gene turn on? The environment, vitality, you're getting ahead of us here. But that's true. Exactly. So what happens here is we have what's called a promoter region. A promoter region. So we have a site upstream from the gene, right? If you have a gene, to your left is what's called upstream, to your right is what's called downstream. So upstream of this gene, we have a promoter region. And this is an area where we turn on the gene. To encode the gene, we need something called RNA polymerase 2. RNA Pol 2. Do you guys love RNA Pol 2 as much as I do? I have a crush on RNA Pol 2. I mean, you know, if we had our journal club, which I'm seriously thinking about starting, who would join my journal club if we do it? Oh, look at that. We already have some members. I love RNA Pol 2. You think about it. It has, how many different enzymes are in RNA Pol 2? I think it's like 47 or something like that. All these really cool enzymes that are connected together. They come together in certain processes, and they can actually shift in different configurations depending on the gene that you're trying to activate and whatnot. So RNA Pol 2 comes down and it binds to this and we turn on the gene. But RNA Pol 2 just doesn't come down by itself. It needs to be recruited. You know, like that grumpy teenager in her bedroom. You need to recruit her and get her to come out, right? So we need to do things to get RNA Pol 2 to come out. How do we do that?
Incentives.
What's that?
Incentives.
Incentives. We need to give it incentives. Yes. And in this case, those incentives are other molecules, right? So there's different molecules. So what happens is they attach to RNA Pol 2. RNA Pol 2 comes down. It forms this beautiful structure on this promoter region. It activates the promoter, turns on the gene, and then boom, we get protein made, we get GLP-1 made, insulin levels go down, glucose levels are attenuated, and a lot of good things happen, including weight loss, right? So this is what happens. This is activating a gene. Okay, but these guys right here, how are these guys recruited? How do they just show up right here? Yes, molecules. Yes, exactly, molecules. So what happens, and what's really cool, is this molecule, EGCG, can actually, of itself, it can bind through something called signal transduction cascades. And these signal transduction cascades can then recruit and cause these to be present at the promoter region. And these present at the promoter region bind other ones to it, other ones to it, other ones to it, until it grabs RNA pol 2, boom. Now we got a protein being made. What happens if you don't have this? Right? No this, no dice. That doesn't happen. And so, what happens or doesn't happen if you're not making a gene? It shuts down. If you don't have GLP-1, it shuts down. And what happens to the body in general if it can't make the gene that it needs, the protein that it needs to make?
Increase weight.
Increase weight. What else?
Increase insulin.
Increase insulin. Good. That's specifically for this gene, GLP-1. But what about
BDNF.
genes? Dysfunction and disease. Exactly. Dysfunction and disease happens if you can't turn on genes. It's that simple. Okay. Oh, I don't want to erase you. You're too cute. Well, let's come over here. Whoa, Nellie, that's another reason we don't like this guy. Does anyone have a chisel? Okay. So, we talked about genes being turned on, but we have our gene again. Let's say another gene. What gene do we want to talk about? Someone mentioned BDNF. Fantastic gene. Who here has heard of BDNF? BDNF is just as important as GLP-1 to human health, right? We got some cheering back there. Exactly. BDNF is actually more important than GLP-1. That is a bold statement. Isn't that a bold statement? It might be true though. We'll see. Okay, so we have this gene, BDNF. Now, there's another thing that can happen. What can happen with this gene is we have genes that are stuck in the on position, right? So what happens is we have our promoter region and we have RNA pol 2 and all these beautiful molecules here, and they're just cranking and making that gene. Full speed, full bore all the time. Is that a good thing? No, right? So what do? I was going to say Chinese, what do we do? I dreamt in Chinese the other night. It was really concerning. But anyway, the dream was kind of weird. Anyway, so this RNA pol 2 is bound to this promoter region, right? This here, this is bad. This is bad, right? Right here. Sometimes it's good, right? This is what you want. But sometimes it doesn't come off. Why wouldn't it come off? It's stuck. Why is it stuck? Because you need molecules to recruit this and turn it on, right? What about turning it off? Do you need molecules? Would it make sense if you need molecules to turn on, you need molecules to turn it off? Absolutely. You need molecules to turn this off. If you don't have molecules there, then what happens? It just stays on all the time. Now, is BDNF a good gene?
Yeah.
Oh, yeah. Baby, yeah, it's a great gene, right? But if it's turned on all the time, is that good? No. So we want it to turn off. So we need molecules to turn it off. And a great molecule that turns it off, trying to remember. Can I draw curcumin off the top of my head? Dr. Schneider can. Dr. Schneider, can you draw the chemical structure of curcumin off the top of my head? I think it's this. But we'll do 1, 2, yes, baby, yes. Okay, this is curcumin. I really think it is. I think that is curcumin. Maybe there's a hydroxy. Let's just do. I think that looks a little naked. Let's see. Okay, now that's curcumin. Great, curcumin. Powerful molecule. And curcumin is a molecule that binds to and helps to regulate BDNF. Now, one thing that these molecules do is not only do they help recruit, but when it's time to turn it off, these molecules can actually grab the promoter and cause it to disintegrate into all of its little components. And all these little components can be upcycled again to be recruited to turn on the gene. So this is how it works. So not only are molecules important in turning genes on, they're important in turning genes off. So when you move this away, this gene is not made. That protein is not made. And that's good. So we turn genes on, we turn genes off with molecules. How many molecules are in the world today? How many molecules on average are in a plant? These medicinal organic molecules. If you just take a normal run-of-the-mill plant and you look for all of its molecules, how many molecules are in a plant on average? Billion? Maybe, I would say maybe if you run it through, and we're just kind of riffing here a little bit, I would say probably 600 to 800 molecules in a plant when you really look at it. Okay, 6 to 800, we'll just say 700, right? 700, that's a good number. 700 molecules. How many species of plants on the earth? 600,000. Okay, 600,000, got it. 700 molecules in a plant. Now that's species of plants, right? How many plants are in a species? There's a lot, right? So we're just having fun here, right? Maybe let's say there's 3 million, right? 600,000 species, we'll just keep it simple. 3 million plants on the planet. If each of them has 700 molecules, how many molecules is that? What's 3 million times 700? Huh? What? Who's done the math for us? I mean, some of you guys, I'm sure it's like, just calculator. Spit it out. What is it?
2 billion.
No, I want a number. What's that? 21 million? 21 billion. I'm looking at Greg. 21 billion? Is that right, Greg? 2.1 billion. Okay. Greg knows his numbers. 2.1 billion molecules. Now that's assuming all the molecules are different, right? If we pare it down, I don't know, maybe we're at 200 million molecules. 200 million molecules. Is that crazy? How many molecules have we discovered so far? If you go into SciFinder, which is like my favorite thing to do, people look at Instagram, I go to SciFinder. SciFinder, you could actually look at all the new molecules. Isn't that cool? You can actually filter and say, hey, what are the new molecules that have been discovered and published the last, 6 months? And some will pop up, the last 2 years. Isn't that cool? I encourage you to go give it a try. I mean, forget your Netflix subscription. You should all subscribe to SciFinder. It's so much fun. You could just sit in bed. That's what I do. I sit in bed and I look at new molecules from SciFinder. Isn't that sweet? So much better than binge watching something. Anyways, so, when you look at SciFinder being, maybe 200,000. No. Probably 20,000 molecules have been discovered. 20,000. I'll have to go look. When I looked a little bit ago, it was like 19,000 something. So 20,000 molecules have been discovered. What's our potential here? Let's just say 300 million. Okay? 300 million. And we've discovered 20,000. Let's just say 20,000. Okay? What percent of 300 million is 20,000? What is it? Huh? 1%? Less than 1%, right? Less than 1%. What is it? 0.0067%. Good. A number. 0.0067%. We love numbers, right? We're professionals. We're scientists. We don't just need, we need a number. Okay. 0.0067%. Why did we go through that exercise? What does this mean? There is so much left to be discovered and explored. Look at that, 0.0067. That means we have a job still here at 3 International, right? That means we're not going to be in the unemployment line, right? what we're doing is so significant. New molecules. And we've talked about it before. New molecules from where? All around the world. All around the world. You know, you think that, so there's a drug that's used for HIV, and this drug was actually a derivative of Baker's tick. Baker's tick is a plant that is a weed. It grows on the side of the road. When you disturb the road, you know, from construction and stuff like that, you disturb the road, and this plant grows after you disturb the soil. It's a weed plant. But from this plant is a molecule that can help with HIV treatment. I love that example because it goes to show that all around us, even some crazy weed growing on the side of the road that people think is a problem, that people think is a hassle, this plant contains powerful medicinal molecules. Okay? So that's what we do here at 3. Okay. Does that make sense? Okay, good. All right. So we're going to leave up our beautiful molecule because that's too beautiful to erase. And we're going to make sure that the production team never erases this, ever. Dig around the back. Okay, just kidding. So, EGCG. This is a great molecule. It's a powerful molecule. It regulates genes related to energy, cognition. I don't know. No, I was going to say something, but I won't. But it's really important. It's really important. And we'll talk more about it maybe later. Maybe. Okay, so EGCG, great molecule. It has carbon, has oxygen. Okay, let's draw the structure of water. We know that, right? Okay. Are these two molecules similar to each other? Just look at them. Are those similar? No, they're not, right? Like dissolves like, right? That's one of the dogmas of biology. Like dissolves like associates with like. So are these two similar? No. Do they associate with each other? No. Do they dissolve each other? No. Okay? What percentage of the human body is water? 98%, 70, right? I mean, they say somewhere from 60 to 80%. I don't know, whatever. It's a big number, right? Oh, I just said whatever about my numbers. No, we need to know for sure, right? Okay, we'll just say it's 70. Okay? Now we have a number. Now we feel good because we have an actual number, right? 70% of the body is water. Okay, so if this is 70%, is this going to dissolve in water? No. So does it dissolve in the body? No. If something is not dissolved in the body, is it absorbed in the body? No. Yeah, it's not absorbed. Oh man, but I love this molecule. I want it absorbed in my body, right? Right? I do. I want it. It's beautiful, right? Why wouldn't you want this beautiful molecule in your body? But we don't just want it in our body, we want it in our cells. Because you aren't what you eat, you are what you absorb. Okay. So we want this puppy to be absorbed into the body. So what do? We market it, right? We just say it's absorbable. Yeah, it absorbs. Ta-da! Right? That's what a lot of companies do. They say our products are absorbable. And they have EGCG in them, and we're like, well, how are they absorbable? And they're like, they are. Just trust us. They're absorbable. Like how? They are. Okay? How? Well, we wrote it on the product profile, okay? Well, how? Don't talk to me anymore. Sorry, I just asked a question. So, how are we going to make that absorbable? Electrolytes, okay. Electrolytes is one way, so we can actually bind, excuse me. We can bind, sodium, potassium here. That's a really good answer. Magnesium, right? So electrolytes combined to these oxygen molecules via van der Waals forces. Who loves van der Waals forces? Okay. Van der Waals forces, what? Van der Waals forces are like the coolest thing ever. Maybe that'll be part of our next journal club, right? Van der Waals forces. So you have electrolytes through ionic and non-ionic bonding interactions. Van der Waals forces, whatnot, can make it dissolve. Good, right? So this is a key point. What we're doing is we're changing this structure to look a little bit more like this, just a little bit. Okay, good. What are other things that we can do?
Cellular absorption technologies.
Cellular absorption technologies. Thank you, Dr. Bob. Man, he just took away all my thunder. Gosh, would you stop doing that? Right, so cellular absorption technology. So what we can do is we can do a whole bunch of different things to try to make this molecule more absorbable. And different things that we can do, we can use micelles, we can use liposomes, we could use adjuvants. Thank you so much. Enzymes. We can use what's called polyphenol complexation. And, there's some other things that we can do. Things that have been discovered, and there's probably things that haven't been discovered that we can do to make sure that this molecule is increasing absorption. Which one do we use? All of them. Really? All of them? Yeah, you probably could. Okay. Yeah, because the enzyme could cleave right here. Yeah, that would work. An adjuvants like piperine and menthol, they make the cell membrane a little bit leaky, so the bioactive molecule could go through. Micelles are just a, we draw it like this, where you have a glycerol molecule. Why don't we just draw the structure of glycerol? Sure, why not? Right? Okay, we have glycerol molecule, which is bound to a fatty acid, like this, like this. Oh, I'm sorry. But whatever, it's not, right? So we have something like that, which helps to mimic water in the sense that this is the polar part of the molecule and this is the non-polar part of the molecule. So EGCG, I'd love to just nestle in there like a little baby, nestle in there amidst all of these non-polar alkyl groups, right? So it forms this nice little structure, right? A micelle, if we wanted to just kind of draw large stuff, micelle looks like this. See, isn't chemistry fun? You just get to color. Isn't that great? You just get to color. Okay, so this is a micelle. All right. So what happens is this area is polar, right? And water is water a polar molecule? I'm about to fall over. You bet your bottom dollar. Water is a polar molecule. So what happens is when we have this, which is polar, and this area is nonpolar, what happens, this molecule overall, is this polar or nonpolar overall? Nonpolar. Very good. You guys are so smart. So this molecule is nonpolar. So what it'll do is it'll sit right in there. So it sits right in there, and water surrounds this area, the molecule sits in here, and it's pushed into the cell. Isn't that beautiful? Beautiful chemistry. So what we've done is we've used different cellular absorption technologies. How many absorption technologies do we have in our company? 12. Do we have more in development? Yes. Why, yes, we do. Why? I mean, 12. 12 is a good number, right? Why would you want more? What?
We are three.
We are three. Yes, exactly. We are three. Don't ask. We're just three. Yeah. We don't have. We want to have an even number 13, right? Who was born on Friday the 13th? You were. I was too. There we go. Okay. So, why do we need to use different cellular absorption technologies? Why do we want to discover more? Because the technologies that we have right now are good, but there's still a ways to go. You know, even our cellular absorption technologies that we use in Revive, right? It makes Revive 3 times more absorbable than other supplements. Wouldn't it be good for it to be 9 times? 15 times? 100 times? Yeah, right? So that's what we're doing. We're trying to discover new molecules. And you know, one of the cool things when you travel around the world discovering new molecules is a lot of times the molecules that help to make other molecules absorbable are found together. Right? So when you discover a new molecule from a plant, a lot of times you discover new absorption molecules. How freaking cool is that? So we're doing like 2 things at the same time. Okay, new molecules. What do? We discover new molecules. We make those molecules highly absorbable. Because new molecules equals new results. New molecules, new results equals new you. New molecules, new results, new you. Does that make sense? That's what we do here at 3. Okay. SAB members that I'm sending? Okay. While you're thinking about that. Well, when we have a new molecule, how do we know that it's actually good? Like I'm like, ta-da, here's a new molecule. But new molecules can kill you, right? They can. Testing. Wonderful answer. We run our products through different testing. And there's a whole area of science where they've developed tests. They've developed a test to see if a molecule is anti-inflammatory. There's a test to see if it has anti-tuberculosis properties. There's a test to see if it has anti-HIV properties, anti-cancer, and on and on and on and on. So you can buy these tests. And you can basically throw the molecule into the test, and the test will say yes or no. So what we do after we discover the new molecule, we take it back to the lab and we run it through testing to see if that molecule has activity against all different need states. So let's say we're developing a cognitive health product, a brain health product. Yeah, you like that? Okay, all right. I hear you. Okay. So if we want to develop a cognitive health product, we need to find a gene that activates cognitive health. What gene? For instance, we just talked about one, BDNF. So what we want to do is we want to see if we can find a molecule that activates BDNF. So there's tests for that. So that's what we do. That's how we figure out what we're doing. So these plants that we're discovering and studying at the Thailand Medicinal Plant Research Institute, once we collect those plants, we send them down to collaborators in Chiang Rai, and if we can, we export that plant material here to the US, and we run it through assays. It's called bioassay guided screening. That's cool, right? Everybody's like, I'm not impressed. Okay, sorry. But we run it through these screening mechanisms, okay? So that's what we do, in a nutshell. And we pick certain genes. So a lot of people, when they want to develop a product, they actually call a contract manufacturer and say, hey, bro, I want a creatine product. Creatine's hot right now, right? TikTok? Yeah, creatine, I want a creatine product. And what do? Boom. Yeah, we have a creatine product. Do they only give it to me? Do they only give that creatine product to me? If you're a businessman and you make a formula, would you only give it to one person? No way. That's stupid, right? You want to give it to as many people as you can. But what happens if I have that creatine product and they give it to 9 other people? Saturates the market. And what does it do to my power to change the world? It goes down, right? So, we need to find new molecules. The great thing about what we're doing is exclusive. Now, what we're talking about, not molecules, genes, whatever, how many other companies do that? Have you seen another company that does this? Have you? I haven't. If you see one, tell me, because I want to talk to them. Right? Wonderful. Science, third-party testing. Yeah, so what we were getting to, sorry, I was just so excited, I'm all over the place. Clinical testing, results, right? Don't tell me Show me. That's what we say. Don't tell me, show me.